Hello, everybody. Long time no see. Busy life, am I right? Okay, so last time I was streaming, I did the Who Wants to Be an MMLionaire as an environment. Today, what I want to do is I want to make Lykeio not the environment, the API, the unified API environment module library in Python to do that. So there are two things that I want to do. First of all, I want to make Lykeio as a... Sorry, I hope you can't hear that, but I can't turn the windows off, close the windows because it's too damn hot today here. I want to write the Blackjack application for NLP, which I want to transfer into this Lykeio. It was written originally by a friend of mine, another maintainer of Apotheki, but he gave me permission to do everything, unify everything under one package and serve it under the GPL. I will talk more about that later. And we're also, if we have enough time, we're transferring MMLionaire, we're moving Blackjack, and if we have enough time, we will do an MCP server for Lykeio in general to have everything so that LLMs can use the environment to train on, apart from using it only for reinforcement learning. So let's start. So first of all, let's go to projects and start new Lykeio. So why Lykeio? Lykeio in Greece is the high school effectively. So if agents have to go to the gym, to the environment gym from OpenAI in Farama, then they should go to Lykeio to learn how to speak and to do stuff with language. That's the idea. So let's go cd Lykeio. Wait here. Cd Lykeio. So why poetry and not UV also is a good question that people might ask. I'm not very familiar with UV's build process, if there are. I tried using that and I run into some issues with how you build the system in general, but in any case, we have, so if we see, we have the source, we have PyProject and everything, we have the tests. Okay, so I'm going to reference what my colleague, co-maintainer, friend, whatever, has already built in order to start working from that. So my friend is using UV. Well, wait, first of all, we have to do the basic stuff. Yep, git init. We'll be using our own hosting service, Apotheki, erga.apotheki, where you can find all of the other projects that we have. And we will also mirror it on GitHub. It will be on GitHub as a mirror and not mainly on GitHub because it feels better to know that we can do anything in-house and host it. It's very simple to run like this kind of thing. So so let's grab the license that we are going to use. We have a mixed license here. I will explain what this is. This is the GPL v3. Everybody knows the GPL. So let's go projects, Lykeio, and here we can just add a folder. It says add it here. And this is the training public license that I wrote myself. And the idea is that, okay, that is gone. The idea of the TPL, the training public license, is that this code and content is licensed under GPL v3 or later, with the added condition of if this code is used for training an LLM or fine-tuning an LLM, the LLM and the weights have to be released under the GPL. So effectively, it's please honor the GPL even in this situation type of thing. Because the GPL, if we check, it says that the GNU publicly, blah blah blah. So if you go to the terms and conditions, it has to do with essentially you have to use derivatives. If you make a derivative work, then it should be GPL. And so I feel like training a model is making something sort of a derivative. So I just want to enforce that a bit more with the TPL. But in any case, we have that. So if we do ls, yeah. So yeah. So we will. I'm not going to make it now because I will have to do some SH keys, because this is not my main dev device. My laptop, which is on the side here, is that. But it doesn't really matter. Anyway, so we have the licenses. The README is not going to be there for long. Let's set up the Pi project. So poetry add. It should have the MCP as a thing, because we're going to build MCP pretty soon. Do I need anything else to add? Let me 1 second check what I have done. Over here it should be, yeah, there is nothing else to add. Okay, so all right, so we can go to okay, so cd source Lykeio, yeah, here. So we're going to do a couple of things. The first thing is that we're going to have let's start touching things. Wait, so we have the init. Okay, so we have to touch. I'm looking there because I'm using a TV. I don't have a good display, so I'm using a TV, and the microphone's over here and it's blocking the view. So I have to lean a bit because the table isn't big enough. So we want to touch the core.py and we want to touch the base.py. And these two, the core is the core of Lykeio, from which the different environments are built. So it will have the different classes that we're going to use, the different types essentially, which are going to be the state description, the actions, so that an LLM or an Electro or reinforcement learning environment can both use this to learn. You'll see as we build it how it works. And then base.py is more of how the base class of yeah, so what the base class of the Lykeio environment should look like. So let's start with the core. So the core classes essentially. So let's use Helix core. Yep. Okay. So let's start by maybe can I do? Yep. Let's make it bigger. Let me see how it seems on stream. I think this is a bit better in order to be able to see what's going on. Also, 1 second, let me see if I can do, because, yeah, 1 second. Nope, 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 nope. Nope, nope, nope. Streaming tools, nope. Manager, yeah, okay. I think this is it. This should be it. Yep, everything is here. I'm muted perfectly so I don't listen to myself and you don't listen to me multiple times. So I should have probably fixed that before already, but yeah, let me also, yeah, making NLP, the title is correct, software, yeah, okay, so everything is correct. ML, let me, yeah, okay. Alright, so let's go. We have the core, and so what we want to do is that we want to start with class state description. I'm going to reference outside of the screen. So the idea is that we take what my friend has made on the core and the base, what the other maintainer has made, and we sort of transfer it here so you can see how it's done, and like you can have everything. And then we're going to go back to MMLUnir, transfer it, and then we're going to build the Blackjack and maybe the MCP server, as I already said. So this is a class to represent the current state in natural language. Yep, okay. And then here we have the def, the init. Man, I'm very happy that I found this monofont, to be honest. Description, it looks real nice. String, okay. And so it takes in a description, a string, a description of the environment, and if not, okay, so types in Python suck. So if not is instance, so we have to enforce that the fact we say here that the description should be a string, but because it's Python we have to enforce again that it's a string. Raise value error, sorry. So raise the value error that this state description must be a string, must be, I mean, type string, full stop for grammatical stuff that nobody cares. Iced coffee, Freddo espresso, to be honest, but you know. And then it should just say that self description is the description, so that it is passed to the other methods of the state description. So so the string self it returns returns a string, and it just return self description, and the def wrapper self, I mean, it that returns a string and returns f description equals to self dot description r. Yep. Okay. So this is the class for the state description. So this is the state, gets described. It obviously this is not like, this is the baseline, so that we have the class, the type of state description, in order to be able to instantiate and return stuff as a state description in natural language. And we also have the class action. So this is, there's probably a better way to do this, but you know, so represents an action in language environments, full stop. Oh yeah, that we don't need that. Okay, so let me move something so I have more space for my hand. So yeah, the init process takes the self and takes action, which is any type, because it can be, I mean, it should be, no, it cannot return whatever. It's any, just to be safe, and description as a string, and it should be, your args should be of action, actionable input, e.g. example, an int, and a description. It is human double, not human readable. I prefer the natural language description of the action, comma here, I guess. I mean, I don't know how people do it. This seems correct grammatically, but anyway. And the thing that it initializes is self.action, which is equal to the action, and the self description, which is equal to the description, and that is all. Yep. And then we have the EQ method, self other, and that is if is instance other action. What we want to do is to return self action is equal to other action, so a boolean, and then otherwise return false. Okay, so also we want the has to have an input of self and return the has of self action. Yeah, and we want the wrapper, the wrapper self to be to return f action equals self action, and the description equals to the string, so it should be the I don't know how do you call them in English, but like the lines are helpful to showcase to the user that this is a string. So self description, and here we go. We have everything we need. We have both the action and the state description, so we're ready on that. And now we can move on to the base. Okay, helix base. This stream might be less me thinking and more copying and doing stuff. Obviously, I mean, this should be its own branch, but like this is the base, so I can do it on the master branch, and then I can just do the other branches for everything else, and then merge them together on our own home server, and then clone that on GitHub or whatever. But anyway, so we want to do the base now. So we want to use ABC because we want to create abstract classes. So from ABC import ABC and abstract method, the decorator, and we also want from this is going to be Python 13, so we don't need typing. We don't, because all of those are given from Python, the core library from the start. And we also want from .core import state description and action. Yep, perfect. And so class, how should I call them? My co-maintainer, Tolios, Tianzi, I don't know how to pronounce, how to call him, rather, not pronounce, I know how to pronounce his name, has them as language games. I wanted, back in the day when I started having this idea, I want to call them classes or courses, because when you go to high school you have courses, so I might go with that. Honestly, I don't think he will be that annoyed, because it's in gymnasium they're called Envs, and they're just like, so I'm thinking I will go with courses, and we might change the name. It doesn't matter anyway for the end user, because this is just me toying around with stuff. So class course, and it should inherit the ABC. And so let's give a docstring. This is the base and base class for language based, for natural language envs. Courses, wait, I mean base course would be better. courses can inherit this to define courses. Full stop. Yeah. Okay. So let's start with the init. Self. We don't need anything else. We just instantiate this because we care about the other functions, that the other methods of the class, which will be abstract methods. So we have the super. I mean, I prefer the new way to type it. Base course self init. Yep, and self current state equals to none. So at the beginning there is no defined state or state description. So the first thing that every environment, this is drawing from how Gymnasium works. Gymnasium has basically 3 mandatory methods that you need to have. The first is to reset. So after each episode, you need to reset to the initial conditions. So you need a reset class. So that's what we're going to make now. Abstract method, def reset self, whatever else, and this will return a state description and for now pass. The other thing that we need to make is a step. So the way that reinforcement learning works, for anybody that might not know, or how an environment works in general, a game, any type of game like Blackjack works the same thing, is that you have the state given to the agent generates an action, and then that action is given to the environment, so the agent acts on the environment with that action, and then that environment gives you a reward. So was that correct or not, essentially. You can use LLMs on this also, because you can have them zero-shot a solution, then you can compare, because you can just have them auto-regressively run for like until they give an answer, and you can then use that answer, which is what the MCP server is for, essentially. Like the MCP server will just force the agent to comply to the API that we're building right now. So it needs a step method, step, which is self, and also needs an action from the agent, or LLM agent, or reinforcement learning agent, and it should return a tuple. That tuple is okay, so what we need to return as output is the next step of the environment. So based on the action that the agent took, is how did this change the environment. We want to have a reward, so that is either an integer or a floating point, depending on how you build the environment. So it should be a number, because that's how tensors tend to work better. It should return also done. So is this the end? Has the agent won or not won, or died, or whatever in the game that you're playing? So that's back in the day, OpenAI had that as done equals is a boolean, but now Farama has changed that to truncated and terminated. So I'm going to use that. So we're going to return 2 boolean states. We're going to use I mean, I might as well write it. So we have the first thing that is the next step, so that's a state description. Then we have the reward, which is type int or float, and then you have truncated, terminated, or however you want. I prefer truncated and terminated side by side in this order, because otherwise it's a bit confusing. And then you have any extra info that you might want to pass back, which is mostly for humans or for anything that has to do with the environment. So that's a dictionary of type any. I think this is the correct way to do this. And yeah, pass. And let's give some docstrings for completeness. So this resets the environment to initial state, returns the initial state description. Okay, perfect. And this is the step. So this is iterates. It should be iterates. Yeah, iterates. I mean, it's not iterates necessarily. It could be. Yeah, I mean, moves a single time step, moves the environment, meant a single time step based on the action, returns. It should be state. Wait, I mean, yeah, returns as tuple, and if we have, I mean, I'll do it right like this, just so it's more clear it's a tuple, I guess, and should be state and reward truncated terminated info. So it should be this, and we have a pass. It should also have okay, so this is a thing that I guess it's for LLMs mostly, that my co-maintainer, my friend, has added another abstract method of available actions, which returns, so it's a way to return the list. Yeah, okay, that works. So that when we query, because here it should have the number of actions also, but you can also just do the available actions because it's a list. So we could do self dot action space is equal to self or something, and oh yeah, I mean, yeah, it's state. So wait, len like this. Yeah, okay, so abstract method and the available actions. So that takes self, and it should return a list of actions. Yep, and it should return, if we don't define anything, it should return just an empty string if there are no available actions, effectively. So if we don't define it, so we need to define it every time. So it should a list of available actions. Perfect. And there is also another self-describe, but there is no need for that, I don't feel. Maybe I will go back. So anyway, we have the base course ready. We take the abstract class and create some abstract classes in order to go. Yep, to have that. Okay, and let's start doing the actual nice things. So let's start working on the Blackjack. So so we have these. We should make dir courses, new courses. Okay, the way that it's currently implemented is that it uses the my maintainer, my co-maintainer, not my maintainer. I don't pay him, nor do I pay myself for the matter. Anyway, the way that this works is that we have different folders for different types of games. So this Blackjack would be a card game. So let's make that, I guess. Yeah. Card games. The card games, because you could also make a trading card game. You could like import some base cards, maybe from Magic the Gathering or from Hearthstone or Yu-Gi-Oh or whatever, or make your own and just have that as a card game that the agent can play and train against. Like, because you have chess you don't need a text description, but card games you have text descriptions, and this will work very well with that. So maybe another stream idea at some point in the future. Or just in general, an idea for the Lykeio would be to make a card game. Maybe like use early Hearthstone cards because they're the simplest to implement, as in they just deal 1 damage, etc. And we could have that. So yeah, let's start working with the Blackjack thing. Well, first of all, we need to touch init here. I will fix that later at the class. So let's helix blackjack.py. Yeah, this I've edited stuff here already, so the names exist, but not on this folder. So we're now transferring everything, we're aggregating everything together to make use of. So we need to import random because we're going to shuffle things. We don't need typing, so from core import state description and action, and from base import that should be the course, base course. Yeah, okay, perfect. And okay, so we need, well, okay, so what we need to do is to build the following. We need to have a way to create a deck, we need to shuffle the deck, and we need to give the cards to the player and to the house. And so let's start with that. First of all, we need to make the class, obviously. Let's leave an extra space because that makes the linter happy. Zack course, and it inherits the base course. Wait, here, base course. And so we define, course to teach an agent to play blackjack. Okay, so something about this. We did try this environment that I'm copying now with an lecture. So the natural language reinforcement learning models that we implemented, that I wrote, and it turns out to actually work. I'm very happy for that. I'm very excited because you can teach reinforcement learning agent, proximal policy optimization agent, to play blackjack using natural language. You will see exactly the prompts that we used. You can maybe generalize the prompts to make it even more generalizable to play blackjack effectively. But yeah, that it works. And so we have an agent that can play win on average. I think on average it has a score of minus 0.09, which means that it's not as optimal as the best player. It hasn't found the best thing, but that could be also due to having a single seed, and if we average over many seeds, then maybe it would do better. But yeah, it works. So you will see how it works, and then maybe at the end I might show you the graph of it working, which is really nice and really interesting. So yeah, we have the course. Now we need to def the init class. We define the init class, and it does not take any arguments, and we just have the super method of blackjack given the self, right, dot init. Yep. Okay, and we also start with the player hand is an empty array, and the house, the dealer or house dealer hand is equal to an empty array also. And we need to define this method that we'll do right now. Self, the deck that we're going to use is going to be made by the function of shuffle deck, and we also need the current state, which is defined already, but it doesn't hurt to have it written explicitly. So it's more readable this way if anybody wants to go in and make any changes. Okay, so we have we need to create the deck. We need to create and shuffle the deck, which, yeah. So we have the def shuffle deck. It takes self, it doesn't take any arguments because we just create it out of thin air. It doesn't, it's one deck. We're going to play with one shoe. One shoe means one deck in Blackjack, in case anybody cares. Wait, okay, so it should return a list of integers, and it has initializes a deck of cards and then shuffles it. Yeah, okay, so we have the deck, which is an empty array, and then we have the values that the deck can take. Wait, okay, give me 1 second, I'm going to be right back, but for now I need to mute because I need to answer the phone. Sorry for that, we're back. Yeah, so where were we? We were shuffling the deck. So the values, the possible values that we can have is the ace. And we have, wait, I mean, I prefer this notation for me. Since Python doesn't care, I find it a bit easier on the eye. So we have then we have number 2, we have number 3, we have number 4, we have number 5, you know the drill, 6, 7, 8, 9, and then we have the 10 and the jack and the queen and the king. Yeah, okay, perfect. And then we have also the suits, I don't know, so it should be hearts, clubs, spades, and diamonds. Okay, perfect. And then we have a simple for loop, double nested for loop in suits, for value in values, deck append, and we want to append the tuple, yeah, the tuple of value suit, and that should create just the hearts, ace of hearts, etc. It should put everything in a line, and then we shuffle. It's random.shuffle deck, and we return the deck. And here we have the deck. Everything is shuffled. Everything is perfect. So we now need to move. We now need to move to the next part where we deal the hands. We deal a single card. Sorry, because every time step, if we will be able to choose if we hit or if we stand. We're going to make the simplest thing. We're not going to add the other rules of Blackjack. It's a very simple use environment. Every time, after every hand, we reshuffle, so there is no counting or long-term strategy. Every hand we shuffle, and you can only hit or stand. There's no doubling. There's no I don't remember the other things. I don't play Blackjack. We need to be able to deal a card with self, and it should be a hand, where hand is going to be a list of integers, and it should deal a single card to a given hand. Okay, and what that does is hand append, because it's going to be a list. We're going to append a pop of the deck. So we need to return that. I mean, no, we don't need to return that because we're just appending to the hand. So we're going to use that, yeah, because it just, yeah, okay, whatever. So we have hand value being self hand is going to be a list of int again, and it is going to return an int. It's going to be the total, the sum of the values. So of the cards, calculate the best possible value for a given hand. And we say possible, best possible, because you have the ace, which can count either as for a 1 or for an 11, and you can, like, I mean, essentially, if it makes you go over 21, then it counts as 1. If when you count it as an 11, it takes you over 21, then it counts as 1. Otherwise, it counts as an 11. So this is essentially what we're going to do. So vals is equal to the values of the cards are going to be, if it's an ace, it should be I mean, let's do it like, let's not make a huge vertical dict, right? But at the same time, I mean, let's use the other notation. I think it's going to make it a bit clearer because we're going to use strings. Yeah, so is going to be a 1, 2 is going to be a 2, a 3 is going to be a 3, and new line, let's try, because it's ace to 10 is 11 cards, and then you have jack, queen, ace, so it's 11, 13, 12, 13, 14, maybe, we'll see if we can have it in a nice way. So the 4 is a 4, a 5 is a 5, a 6 is a 6, so we're going to be at 9 there. 7 is a 7, comma, an 8 is an 8, 9 is a 9, and then you have, yeah, we're going to be 1, doesn't divide itself nicely. 7, I mean 7 by 2, it doesn't look nice, so there's no point. 10 is a 10, jack is a 10, a queen is a 10, and the king is a 10. I'm going in, we could do this. I don't know which looks better, doesn't really does not matter. So the value of the hand value, and let's make it a bit nicer. Values here, the hand value. I prefer more verbal, more descriptive variable names than just vowels. I prefer values for no other reason than it helps me. It makes it a bit more readable, I feel like. So that is going to be vowels values. I0, yeah, because we're going to the ith element and we're going to pick that. For I in hand, I mean, you can probably do values item or something, but I need to play for like 5 seconds to figure that out. I need to open a new interpreter and run that there to check, and I'm too lazy. So I know that this works, we're keeping it like that, even though it might be a bit ugly. It might not be very Pythonic or whatever. And then you just have the sum of the total. Yep. And so, not the total, this is the sum of the hand value. Sorry. This is, so the total, so the player at any point has the sum of the value of the cards in his hand. But if he has an ace, so if I mean, yeah, let's, if we could do a in hand, but let's also do if 1 in hand. No, I prefer the other thing. If a in hand and the total, if the total is bigger than 21, if it's bigger than 21, it values for 1, so we're not going to change that. And if total is less or equal to 11 or to 10, because the ace takes you, if less or equal to 10, or wait, plus 10 is less or equal to 21, so blackjack, and then we treat the ace as have I put no return total plus 10, otherwise return total. So if the ace should count as an 11, it gets counted as an 11 automatically, otherwise it gets counted as 1. Perfect. So this is how we figure that out, the number of the value. Personally, wait, why is that? Oh, I forgot this here. Personally, I put these values, the internal methods, underneath the normal methods. So I will do that. So we need to set the reset function which returns a state description class. Let's move these out of the way. Honestly, we don't really need to see them. So when we call reset, it should return a state description. Sorry for scratching my nose, it's pollen allergy stuff. I'm not used to the type of pollen in North Europe. Hey, so when we reset the game, to the initial state. I mean state, because the state description is what we return. So we want to return. Okay, so there are two different ways to return something. Let's do the reset first. So what we want to do for the reset is that we just want to reshuffle the deck. So self deck is self shuffle deck. Wait, self action space is going to be also wait, how did I call that? Let's try, and we have here the base, we have the available actions. Yep. Wait, okay, let's open it so I can reference it all the time, because now we're going to go into the stuff, nitty gritty. Len of the self available actions. Yep. Okay, wait, it needs to run. Yep. Okay, so we need to shuffle the deck, and we also need to reset the agent hands, the player and dealer hand. So actually, let me just copy paste this, and yeah, so it resets the game state, and then the game starts. The way that blackjack works is that the player gets dealt 2 hands and the 2 cards, and the dealer is dealt 2 cards. So we run the deal card function on the player hand. So we have shuffled everything, and then deal card to the self player hand twice, and then twice more to the dealer hand. So dealer hand and dealer hand, and then we return the state description. Okay, so this state description is not just a simple thing, so we'll need to define our own internal method for that. So let's return state description. So let's get the state description, because we have the self player hand, the dealer hand. So let's define that. State description. So that returns for us a state description object, and we have the doc script string that says that this should returns the state description in natural language. Yeah, perfect. So we have that this thing, this function, this method should return a natural language description of the state, so of the hand and the value that we have and everything. So we calculate the player total is equal to the self.hand value. We defined that already, given the player hand, here self player hand, and the dealer total is self hand value again. Oh fuck, yeah, given the dealer hand. And now the state description is going to be a big string, and then at the end we're going to return a class, state description class, with the description. Description is going to be our description, and close parentheses. Perfect. So the description is going to be the following. I'm going to use this to do it. So okay, so now we're prompting an LLM, we're prompting the elector on the state description. So what we want to do is to say every time we prompt the agent, we want to say like, hey, you are playing blackjack. These are the rules of blackjack in a very simplistic fashion, so that you don't need to depend on the LLM knowing what blackjack is, like seeing the data. So you can use this not only for fine-tuning an agent, you can also use this to train an LLM style thing to play blackjack, and you can train it on many different language environments, maybe, hopefully, to do things. Anyway, so what we're doing, I mean, for the reinforcement learning with natural language stuff, you need at every time to give it a very extensive thing, and then you hope that it starts understanding which tokens are significant based on the transformer architecture of the agent itself. So you are playing blackjack. The goal is to have a value of 20. I mean, it's not to have, it's to get a value as close to 21 as possible. Okay, so because we're going to go very far off, let me start doing that. As possible, full stop here. Yep, and now each card has a value as equal to its number. Yeah, okay. Face cards are worth 10. Aces count as are worth 11 or 1. Perfect. Oh, it should be an F string. So let me here. Your consists of self player hand. So we give the information to the agent what your hand, the hand of the agent is, with a total value of player total. I mean, we don't need the new line there. It's going to go a bit off, but it is, I don't care. And then the dealer, we need, dealer shown. Okay, yeah, because the dealer has only the first card. You can only see the first card. Yep, I forgot about that. Dealer card, let's say, shows you a dealer card. Okay, and that is not the hand value. So, I mean, yeah, no, it's not the hand value. It's the first card that he has, so 0 here. So the dealer card is that. So dealer has or shows you a, the deck. I mean, you can have this deck still contains, in terms of, you could do more hands. You could do more hands per deck, and then maybe you can learn card counting strategies. But anyway, we will have that just in case that we may want later to give it the ability to do more card counting. Maybe still has, and we don't really, I mean, this just generates more noise and more tokens that need to go to the GPU in the as embeddings, which could, let's not do that. And let's do here, should we return, do you want to hit or stand? Do we have to tell them what to do? I don't think so, because that should be in the, that should be on the action. That should be, wait, core, that should be here, like on the description of the action. So I don't think we need to do that. So in any case, we can just change it at any point anyways. So this is the state description. So when we reset, we have this is the state description. You're playing blackjack, the goal is to get, this is the prompt for the agent, effectively. Not effectively, this is the true prompt for the agent. Now we need to implement we have the reset. Wait, this is an internal method, so it gets bunched up with the others. Let's go down here. Yep, and let's send you down now. And we have the reset, and here we want to make the step self action, which is of type action, and should return the tuple that we said before of state description, the int or float, and boolean and boolean. Right, we have it. Let me here. It should be a dictionary of string and any key string and any item. So okay, processes the player's action and updates the game state. Wait, I don't need those. Yep. Okay. Yes. Okay. And so we have the action string. So okay, so we have the action. The action is let's see here. No. Okay. So wait. Yeah. So the action is a class with an action, which is an integer, or a string or whatever. You can define it however you want. Wait. And then you have the description of the action, which is a natural language description here. So for here, in this case, the actions are going to be integers, because you can either do a hit or stand. But if you might want to have a string, you might want to have if you have continuous space. Although continuous space in as a natural language environment is going to be pretty difficult because I mean you could say turn slightly left at some point, but you know, so you have the action. Wait, the action string is going to be the, not the string, but like, yeah, the action. Let's say that the action is going to be the action dot action dot lower. Wait. Ah, yes, I see how he did it. Okay, so the action is going to be an integer, so that no, it's going to be a string, so that the LLM can choose whether or not it's going to be a hit or a stand. And so what we want is we want to extract that. So this is going to be a string, and it's going to be, okay, action string is hit or stand. So it's going to be either of those, because the agent will have to choose whether to hit or stand, and will have to give it explicitly. Because if you're training an LLM, you want to have it to say hit or stand. You don't want to say 1 or 0. If you have a reinforcement learning agent, this is going to be an action space of 2. So you just use integers, and then the integers, it's just which one of the 2 you choose from the array of available actions. So next time we might write the example, but in any case, it's already on GitHub. It's not on GitHub. Do I have it on GitHub? Do I have it on GitHub? I think not. It should probably be, wait, it's the electors. So yeah, it's not there. Yeah, it doesn't exist. So I might mirror the examples also, but we have here the example for the, no, I haven't posted yet. Okay, I have it on my laptop. The example of how to write the of how to write an environment to train an elector. So I'm going to do that, to show that maybe next time I stream. Hopefully less than a month away from now. A sip of magic potion juice, aka coffee. And so action is going to be either hit or stand. So if action str is hit, we're going to deal a card to the player. Self dot deal, wait, no, deal card to the self player hand. So the player gets dealt an extra hand, and the player total is updated as self hand self player hand. Okay, so this is what happens if the player says hit me. So, and now the new player total has to be calculated. If player total is more than 21, which is the simplest case of you just is more than 21, so then you have return okay, so let's say the reward is going to be -1 because you lost, and you're going to have terminated true. Okay, so in every situation here, let's initialize everything. Terminated truncated equals false. So these two at every time step start as false, and then when the player does something, it takes if it should be true or false. Truncated is always going to be false in our environment, because truncated has to do with the horizon. If you set if the game has dented in 20 time steps, for example, then finish. But here it's always much smaller than that. Usually it's not 20, it's 20,000. If the player spends too much time goofing around, it should end as a time limit. Essentially, that's what truncated means. it should return state description of the fact that you busted, you lost, you went over 21, the dealer wins, and then the reward. I mean, we could say the state here. Okay, well, anyway, in any case, because we're going over the line of the limit of 80 characters, we might as well go here. And then you went over 21, dealer wins. Here, okay, so here, honestly, I would prefer this to be on the right. So let me, and these to be this, so I can go here and do that. So the hand values, yeah. Say description, the big empty space, and the void. So we have the reward, we have two booleans, so terminated, truncated, and then just an empty dict, because we don't have any information to return to the any metadata to the trainer effectively. So yeah, we have that. Otherwise, if the player total is less than 21, then the game goes on. Player might choose again, or I mean, yeah, effectively you return the state of like return state description. Oh, this is not a state description. Yeah, okay, so wait, this is, this is the state description. Oh, you went over 21, the dealer wins, and then you have all of the rest. So let me put this also here. Yeah, okay, so you went over 21, you lost, and then you have the reward, then you have the truncate terminate, and you have the empty. Yeah, okay, so this also here, it should be here. It should be the, yeah, it should not be a class, it should be the self state description function, because that returns the object self state description. The reward is equal to 0 because you haven't achieved anything. Terminated and truncated are both false. So you have then the reward terminated, truncated, and the empty info. You close that, and finally, if you are exactly at 21, return. Okay, so what we're going to do is we're going to assume that if you have blackjack, you win immediately, the dealer doesn't get to play. And we do that because it balances out the average reward, because otherwise it might lead in the earlier testing, if you have only the two options of -1 and 0, that means that if you only pick hit, on average you lose money always, you never win, except for, so if we had this here, if it was like this, then the average reward for hitting is less than the average reward for standing, and the agent just tends to really quickly converge to only standing, because it just bets that the house will lose effectively, which is not what we want. So we want to spread the distribution of rewards in this situation, and to do that we just say that the reward should be equal to 1, and if we have a blackjack and we immediately win at blackjack, effectively you can see this as like, oh, you reached blackjack, congratulations, you stand, and there is no draw in our scenario. So we have the state description of Blackjack, you win. Yeah, with exclamation point, because you win. Congratulations. And the reward, oh, you will also have terminated equals true, terminated, truncated, and the information, which is empty. And otherwise, I mean, let's, for verbosity's sake, we have if the action is hit, and if, oh, I shouldn't have done that. Anyway, if the action is to stand, then we want to do the dealer's turn. So return dealer turn, and that takes nothing as input, and at the end return if neither of those were picked. So if we don't return, if we don't go into the hit or into the stand, this should never happen, but LLMs hallucinate. So it should be state description. It should be a state description. I mean, personally, I would really penalize this if the state description is nothing, if it's wrong, if the action is not either hit or stand. It should be minus 1,000 or something. So let's go minus 1,000. So that is invalid action. Choose. Wait, I should do double here, so I can do hit or stand. Choose between hit or stand. Okay, minus 1,000, terminated, truncated, and then empty info. So, and now we just want to do the dealer's turn. I think that's all that we have to do. We need to the available actions also, the function we have that we so wait, here we have the abstract method of available actions, so we need to have the available actions that so that the agent can be prompted, can be given the appropriate actions. So let's do that. No, let's do the dealer turn first. I think that's better, and then I think I will end it there, because I do feel a bit sick these days, to be honest. Like the change in temperature here is insane. It goes from it goes from like 10 degrees to 20 degrees to 30 degrees in the span of like a week. We have all of the three different weather conditions, and it's like my body can't easily keep up with that. If it's only hot, I can tolerate. If it's 30 degrees, I've grown in that environment, I can tolerate that. But like if it goes to 10 and then immediately to 30, my body goes in a bit of a shock. So I'm in a bit of a shock right now. So I'm going to end there and maybe eat something and relax. So we're not going to do the MMLUNER today, nor the MCP. This will be done at the next stage, at a later date, effectively. There's going to be a part 1 of a multi-series thing. It's, you know, so we have the, yeah, we want to do the dealer, okay, first of all, actions. Yep, and that should be self, and we'll return a list of action class. Yep, pass. Let's do that, and then under here, def the dealer turn self. Yep, okay, it doesn't take an input, and it should return tuple. Because effectively we're returning just like the same thing that we return at the step, because we're returning it here at stand. So we're returning a tuple of state description, reward, so int or float, bool, and dict of string or any. So we have that. I should probably use parentheses, like try and go, I mean, I'll do it later, or I'll do it next time, or I'll do it between now and next time. Anyway, I can remove all this white space now. So this, yep. Okay, so this is going to be the agent, the dealer's turn. So the house. So what this does is deals cards to the dealer. Yeah. So the dealer in Blackjack, when the dealer plays, when everybody else has standed, so this is a 1v1, so it's when the agent stands, you could do it some multi-agent if you had more players. You can make an easily multi-agent setup here where they play against each other, or you could have them exchange information even. I mean, later. So what you can do is say when the dealer plays, he has to deal cards to himself until he reaches 17 or more. So we have the while the value, hand value, the hand value of the dealer, dealer hand is less than 17. I'll do this. Yeah, I'll do this so I can have a bit more space. So while the hand value of the dealer is less than 17, we need to deal cards to the dealer, regardless of what they are. I mean, irregardless. It's here. Sorry. Deal card to the dealer. So self dealer hand is dealt a card, and until it's lower than until it's 17 or higher. And now we have the player total is equal to self hand value, self player total, player hand, and the dealer total and value of the self dealer hand. Oh, it's the first one. Yep. So this, and now you compare the two. If the dealer total is more than 21, sorry, my stomach's a bit irky from all of the coffee. I need to dilute it with some cold water. Or the total is bigger than the dealer total. So if the dealer busts, or if the player has a better hand than the dealer, then we return, then the reward is equal to 1 because the agent wins. Terminated, I mean, in any case here, the terminated is true. Terminated is true. Truncated is false. These two gap. So the terminated is true, truncated is false. So terminated, because it when the dealer plays, like the player has chosen to end their turn. So reward equals to 1 and return state description. The dealer lost, you win, exclamation mark, congratulations, you win. Then reward, then terminated, then truncated, and then the empty info dictionary. Okay, so this happens if dealer total is equal to player total, then it's a draw. so the reward is equal to 0, and we return a state description. Everything else has a space. State description, a draw, nobody wins. I mean, don't need to have the draw, full stop, nobody wins. Okay, and then reward, terminated, truncated, and then the empty dict. And if dealer total is better than the player total and dealer total is less than 21, which is, it is covered from this, but I mean, yeah, it's covered by that, so I don't need to do that. So I don't need to, I don't need the end, sorry. And I'm worse than I thought I was for streaming anyway. So the description is that the dealer wins now. So the reward is -1 because we want to help the agent learn not to lose effectively. And so return state description, the dealer wins, you lose, full stop. Reward, terminated, truncated, yep, okay, and the empty string. And yeah, this is the dealer's turn. The dealer plays with himself, deals cards to themselves, and until they reach 17 or more, and then you compare the scores and the dealer wins or loses. So this is the hand, the turn, and now we just need to do the available actions. So returns the available actions, hit or stand, and it's a very simple thing. So action list is equal to action where the action is hit. And the description is when you choose hit, you request additional card from the dealer, full stop. Yeah, so the way that this works, you have the action, you choose hit, and then in the MCP server or in the environment, when we build the actual interaction, the actual training loop and everything, if you use an LLM, you can choose to pass the descriptions so that the LLM can learn what the action hit does and what the action stand does, regardless or not if it knows the nomenclature effectively. So it should be, do you want to hit or do you want to stand? And then we have another action stand, with a description of when you choose to stand, you decide to end your turn and not take any more cards. And that's all. We need the comma here at the end, and that's the action list, and that's what we return. So we return the action list. So there we have it. We're done. We have the Blackjack environment. So to reiterate, we have the Blackjack blackjack course, the agents learn to play blackjack effectively using natural language. So the way that it works is that you initialize the player's hand and the dealer's hand, and they're both empty. You shuffle the deck, and when you reset, you start again. You deal cards to the player and the dealer, and then you get a state description. The state description is that you're playing blackjack. The goal is to get to a value as close to 21. Each card has a value. Face cards are worth this. Your hands consist of this, and the dealer shows their card. And then you return the state description of this string effectively. And then as the player picks an action based on this description, a hit or a stand, you go through the motions of if he hits, you have this thing happening, then you check the score, and if they choose stand, then the dealer plays, and the dealer's move is to take cards until they have 17 or more, and then you check if they lost, they won, or if it's a tie, and all of that is returned to the agent so that can be stored in memory, in the buffer. I don't know, the experience of the agent in case of reinforcement learning. Otherwise, in case of LLMs, you can wrap it into an MCP or however you want. And so then you have just the methods, internal methods to make that possible. So let's save that. I'm going to stop the stream here because I'm not feeling amazingly well. I should eat something and then rest. So that's what I'm going to do. So thank you very much for joining. See you hopefully soon, where we will now convert also MMLU, because I did that. I didn't have the methods in the same way that I had them here, and we'll also build the MCP server for that, and we also build some other environments. Right now we have already a couple of other environments, higher or lower type of game, which is a card game. So we need to convert that into here also, but we also need to, it was written before we had standardized our development. And there also we have a hold or another guessing game with cards effectively, so we're going to do that. Hot or cold is more of a I pick a number and you have to guess the number effectively by me telling you hot or cold, which is nice because it's an approximate thing with natural language, so the agent has to learn like a hot or cold essentially. But yeah, I'm going to end the stream here. Hope you enjoyed it, and see you soon, hopefully, maybe. Goodbye.